Welcome back to Calculus 1. I'm Dr. Jeff Groh. Today we're going to talk about the first derivative test for relative extrema. First, we need to make some definitions. What does it mean for a function to be increasing on some interval? The function's increasing if, as we go from left to right, in the direction of increasing x values, the y values go up. We say that f is increasing on the set S if for any x1 and x2 that lie within S, where x1 is on the left of x2, this sets up the principle that we're marching from x1 to x2, from left to right, then the height at x1 is less than the height at x2. Well, what does it mean for a function to be decreasing on some interval? You still march from left to right. But in this case, the heights get smaller as you go to the right. I want to bring to your attention the fact that the definition of increasing and the definition of decreasing had nothing to do with any kind of derivative of the function. Indeed, the function may not be differentiable anywhere and still be increasing on some interval. There's a famous example due to Weierstrass of a function that is continuous everywhere, but it is so crinkly it has no points at which you could put a tangent line, differentiable nowhere. So those strange creatures do exist within the realms of mathematics. Our definition had nothing to do with the derivative. However, there is an important theorem. Let f be continuous on the closed and bounded interval AB and differentiable on the open interval AB. If the derivative is positive for all x within the open interval AB, so the slopes are always going up, it has to be increasing. On the closed interval AB, including the endpoints. If f prime of x is less than 0 for all x on the interval AB, then it is decreasing. So, how do we prove this? Choose some points between A and B. We need to see the proof. On part A, we'll suppose the derivative is positive for all x within the open interval AB, and let x1 and x2 be elements of the closed interval AB, where we're assuming that x1 is strictly less than x2. Then f satisfies the hypotheses of the mean value theorem on the interval x1, x2. Therefore, there exists some point C between x1 and x2 such that the derivative at C, which we know to be positive, is equal to the slope of the secant line, f of x2 minus f of x1 over x2 minus x1. Now, x2 minus x1 is positive because we assumed that x2 was to the right of x1. That means the denominator, x2 minus x1, is positive in the difference quotient. We can multiply both sides of the inequality by x2 minus x1 and have 0 is less than f of x2 minus f of x1. Moving f of x1 over, we deduce that f of x1 is smaller than f of x2, but that's exactly what it means to be increasing. x1 and x2 were arbitrary elements of the closed interval AB, so we get increasing across the entire interval. The proof in the case where the derivative is negative gives you decreasing is similar. In our next example, suppose we have 2x cubed minus 3x squared. And I want to find the intervals on which f is increasing and also the intervals on which it is decreasing. The way we do this is we look for places where the derivative is positive and also places where the derivative is negative. Since this function has a derivative that is a polynomial and hence continuous, the only way that the derivative can go from positive to negative or negative to positive is when the derivative is 0. So we're going to look for critical points. Other functions might have places where the derivative can change from positive to negative or negative to positive, where the derivative does not exist. Again, we're looking for critical points. But it's not just critical points, it's also points not in the domain, as we'll see with some examples later on. Or places where you can change from increasing to decreasing or decreasing to increasing are critical points, or points not in the domain, as you will see. The first step in our solution process here is to calculate the derivative, which we will then factor. The derivative is 0 when x equals 0 or 1. The derivative is defined everywhere, so these are the only places that we need to plot on the number line. Those are the only places where the derivative can change from positive to negative or negative to positive, because the derivative is continuous. So it has to continuously go from negative to positive, or from positive to negative through 0. We need to test one point in each of the resulting 3 intervals to see if the derivative is positive there. If the derivative is positive at one point on that interval, it must be positive at all points on that interval. It can only change sign at these critical points here. So if I plot, say, -1, I'll have a negative and a negative. The derivative is positive there. It's positive at that one point, so it's positive across the entire interval. That means it will be increasing on that entire interval. If we plot 1/2, we get positive and negative. The derivative is negative at that one point, so it's negative all across the interval. If we plot, say, 2, we get positive and positive. Note, I don't care about the value. I'm only interested in the sign, positive or negative. We deduce then that this function is increasing from negative infinity to 0 inclusive. It's also increasing from 1 to infinity. It is decreasing from 0 to 1. Notice, increasing and decreasing is something that happens on an interval, not necessarily just at one point. A function, what does it mean to be increasing at a particular point? No, it's between points within a set. 0 and 1 can be included in both the sets where we're increasing and where we're decreasing. Our specific definition for increasing and decreasing permits that. You need to be aware of this fact. A lot of homework programs will require that all of your intervals for increasing and decreasing be expressed as open intervals. In fact, they could be extended to include those endpoints. And 0 could be included both in the increasing interval and in the decreasing interval. And that's okay, because that satisfies the exact definition of increasing and decreasing. Let's do another example. X squared minus 1 all over x to the power 4. Let's calculate the derivative. Derivative of the top is 2x times the bottom minus the top, x squared minus 1, times the derivative of the bottom, which is 4x cubed, divided by the bottom squared. X to the 4th squared is x to the 8th. You multiply those exponents. Remember that when simplifying, you should factor first. We can pull an x to the 3rd out. We can also pull a 2 out. So we have this x cubed that can cancel. We'll have 2 times the quantity, x squared, minus a 2x squared, that's a negative x squared, and then plus 1. So we get 2 times the quantity, 1 minus x squared, divided by x to the 5th. We need to know what the critical points are and also the points not in the domain of the original function. What are the critical points? The critical points are points in the domain where the derivative is either 0 or undefined. You can see that the derivative is undefined at 0, but 0 is not a critical point. It's not a critical point because 0 is not in the domain of the function. You must remember that there are 3 parts to our definition of critical point. A critical point is a point in the domain, that's point number 1, where either the derivative is 0 or the derivative does not exist or is undefined. You can see here then, 0 is a place where the derivative does not exist, but it's not in the domain, so it's not a critical point. The critical points are 1 and negative 1. However, the fact that 0 is not a critical point doesn't mean that we don't plot it on the number line. We do. Because the points you plot on the number line are either critical points or points not in the domain. There's a fine distinction there, and you need to understand that. Now, we need to know where the derivative is positive and where the derivative is negative. So we test one point in each of the resulting 4 intervals. So let's try negative 2. Negative 2 squared is 4. 1 minus 4 is negative 3, but we have a negative in the denominator, because when we raise a negative to a 5th power, we get a negative. Negative over negative, it's positive there. How about at -1/2? The denominator is still negative, but 1 minus a positive 1/4 is positive. We only get one negative there, so the function will be decreasing on the interval between -1 and 0. If we plug in positive 1/2, it'll be positive divided by positive. And note, the derivative did change sign at that point, not in the domain. That point is not, 0 is not a critical point, but it is a place where the slope changes sign. The derivative changed sign there. So we changed from decreasing to increasing at this point, not in the domain. If we plot then 2, we'll get negative over positive, and that's negative. This gives us increasing between -infinity and -1, union from 0 to 1. Take special note of the types of parentheses that I used here. We included the -1, but we did not include 0. We can't include 0 because the function's not even defined at 0. It can't be increasing there if it's not even defined there. Where is the function decreasing? From -1 to 0, including -1, not including 0, and from 1 to infinity. We come now to a theorem that is very important. It has an important sounding name. The first derivative test for relative extrema. The theorem is very easy to describe. It takes a little more effort to be precise in making a statement. The idea is as follows. If the function is going up until it gets to a critical point and then goes down thereafter, if it's increasing before it gets there and decreasing after, then it must have a relative max at that point. That's true even if the critical point is the sort which has a point of non-differentiability. It's still increasing before you get there and decreasing after. You have a relative max. If it's decreasing before you get there and then increasing after, you have a relative min. Same thing if it's a cusp. So, at your critical points, if you're increasing on some interval before you get there and decreasing afterwards, it's a relative max. If you're decreasing on some interval before you get to the critical point and increasing after, it's a relative min. The theorem is stated as follows. Let C be a critical point of f and suppose that f is continuous on a neighborhood AB of C and differentiable on the interval AB except possibly at x equals C. We're allowing for the possibility that C is a critical point where the derivative is undefined. Now, if f prime of x is greater than 0, and hence the function is increasing on the interval from A to C before you get to the critical point C, and f prime of x is negative from C to B after you pass the critical point, then f has a local max at x equals c. Derivative positive, according to the last theorem, means increasing. Derivative negative means decreasing. So you're increasing before you get there, and then decreasing after. It's a local max. Alternatively, if f prime is negative before you get to c, and f prime is positive after c, then f has a local min at x equals c. There is one more case to consider. If f prime has the same sign on these two intervals, then x equals c is neither a relative max nor a relative min. This gives us an excuse to use the neither nor construct, so it's irresistible to write. But we need to say this. If you have the same sign derivative, if you're going up before you get there and you continue on up afterwards, you don't have a local max or a min at x equals c. Similarly, if you're going down before you get there and down afterwards, it's neither a max nor a min at x equals c. The proof goes pretty much as you might anticipate. If f prime of x is greater than 0 on the interval from a to c, then f is increasing on a to c. Also, if f prime is negative on c to b, then f is decreasing on that interval. In fact, we can include the point C on each of these. So we have f of x is less than f of c, less than or equal to f of c for all x between a and c, because we're increasing on that interval. So at the right-hand endpoint, you have to have the highest value. And f greater than or equal to f of x for all x between c and b, because we're decreasing on the other interval. Either way, on the interval from a to c, the highest point occurs at c. Therefore, f of c is greater than or equal to f of x for all x between a and b, but that's what it means to be a local max. The other part follows similarly. And we'll just call it quits at that. It's one thing to conceptualize a theorem. It's another thing to proceduralize it. Let's look at an example. A simple one. X to the power of 2/3. You should know what this function looks like. If you don't, go ahead and pause this video right now and graph it. The graph of this function looks something like this. As you can see, when you calculate the derivative, you get 2/3 x to the minus 1/3. That negative exponent can be eliminated by shoving this down across the division symbol, and we'll have 2 divided by 3 times the cube root of x. This is undefined at 0. So the critical point, there's only one, is at x equals 0. This point is a critical point because it is in the domain of the original function. Remember, critical points are points in the domain where either the derivative is 0 or the derivative does not exist. On our number line for f prime, we'll plot only this one critical point and test the derivative on each side. If I insert a negative number for x into the derivative, I get a negative because the cube root of a negative is a negative. If I plug in a positive, I'll have a positive. So you can see that the function is decreasing until it gets to 0 and then increasing thereafter. We deduce from the first derivative test for relative extrema that f has a local min at x equals 0. But you can see that from the graph. Let's try another example. X plus 9 divided by x. The derivative is 1 minus 9 divided by x squared. Notice that 1 is x squared over x squared. We're subtracting fractions. We should find a common denominator. This gives us x squared minus 9 divided by x squared. Where are the critical points? The critical points are at 3 and negative 3. Don't forget the negative 3. Notice that 0 is not a critical point because it's not in the domain of the function. But that doesn't mean that we don't plot it. Yes, we'll plot 3 and negative 3, but we will also plot points not in the domain, namely 0. Now we'll plot one point within each of the resulting 4 intervals to determine the sign of the derivative. There. At negative 4 squared is 16 minus 9 is positive. Over positive, the denominator will always be positive, and so we get a positive sign for the derivative at each point on the entire interval. If we plug in, say, negative 1, positive, and then negative 1 squared is positive minus 9, we get a negative. If we plug in 1, negative over positive, it's still negative. And if we plot in something like 4, positive over positive, it's positive. Let's see. This function was increasing until it got to negative 3 and decreasing afterwards. It must be a local max. It was decreasing till it got to 3 and then increasing afterwards. It must be a local min. We do get intervals of increasing and intervals of decreasing. It increases from minus infinity to negative 3, union 3 to infinity. And it is decreasing, we need to be careful here, from negative 3 to 0, union 0 to 3. It can't be all the way across, including 0, because the function is not even defined at 0. So we have to leave 0 off of both of these intervals. Our answer is f has a local max at x equals minus 3, and f has a local min at x equals positive 3. Next, let's look at f of x equals x times e to the minus x squared. The derivative requires that we use the product rule. The derivative of the first times the second plus the first times the derivative of the second. The derivative of e to the stuff is e to the stuff, but you need to multiply by the derivative of the inside using the chain rule. We can factor an e to the negative x squared out, yielding 1 minus 2x squared. The only sorts of critical points that we can get are those where the derivative equals 0. So we'll set the derivative equal to 0 and get x equals plus or minus the square root of 2 over 2. You can see that x squared will be equal to 1/2. Taking the square root, x will be plus or minus 1 over the square root of 2. Rationalizing the denominator, you get plus or minus the square root of 2 over 2 as your two critical points. We'll plot these 2 points on the number line. And be careful, we have 2 functions floating around. We're interested in the derivative. We want to know increasing or decreasing on each of these intervals. And that's determined by the derivative according to our theorems. So we'll plug some number like negative. If you're not sure where this number is, just be ridiculous about it. Negative 10 or negative 100, whatever it may be. E to whatever is always positive. So 1 minus 2 times some big number squared, like 10 squared. 1 minus 2 times 100. 1 minus 200, that's definitely negative. If we plot 0 into here, we get a positive number and then negative on the other side. We deduce that you're going down until you get to negative root 2 over 2, so we have a local min there. Up until you get to root 2 over 2 and then down afterwards, so we have a local max at that location. Expressing our answers, f has a local min at x equals negative root 2 over 2 and a local max at x equals positive square root of 2 over 2. We did all of this without graphing the function. You could easily graph this, and you probably should do this on your own first. The graph will look something like this. We can now tell exactly where these extrema are. This local min occurs at negative root 2 over 2, and the local max occurs at positive root 2 over 2. On this next problem, we're going to look at negative cosine x plus 1/2 cosine of 2x. The derivative, and let's constrain ourselves to the interval 0 to 2 pi, just for good measure. The derivative of cosine is negative sine, so we get a negative negative positive sine x. On the next term, yes, we'll get a minus, but we'll get another factor of 2 times this 1/2 by the chain rule. So we end up with the sine of 2x. we can't really mix sine x and sine 2x. We need to use the double angle identity for sine. You need to know the sine of 2x is 2 sine x cosine x. And so we have sine x minus 2 sine x cosine x. From here, we factor. We'll factor sine x out times the quantity 1 minus 2 cosine x. Looking for critical points, we set this equal to 0 and solve for x. That requires using the zero product theorem. Do you remember the zero product theorem? The zero product theorem says that if a times b is 0, then either a is 0 or b is 0 or both. We deduce then that either sine x is 0 or cosine x is 1/2. On this interval, sine x is 0 at x equals 0, pi, and 2 pi. Remember, the sine curve goes through the x-axis at 0, pi, and at 2 pi. This function is defined on a much larger interval, so we can still apply the first derivative test. Where is cosine equal to positive 1/2? Well, the reference angle will be pi over 3. That's the one in the first quadrant. Cosine is positive in quadrants 1 and 4. We can't use negative pi over 3 because negative pi over 3 is not in this interval. Instead, we have to use 5 pi over 3. Now, our interval is from 0 to 2 pi. We're going to have 0, pi, and 2 pi as critical points, but 0 and 2 pi are really endpoints. We have pi over 3 and also 5 pi over 3 as critical points as well. We need to test one point in each of the resulting three intervals in the derivative. So, plotting something like pi over 6, sine is positive. The cosine of pi over 6 is the square root of 3 over 2. The 2's cancel, we end up with 1 minus the square root of 3, which is negative. What happens between pi over 3 and pi? Let's plot something like pi over 2. The sine of pi over 2 is 1. The cosine of pi over 2 is 0. We get a positive value there. If we plot 3 pi over 2 next, the sine of 3 pi over 2 is negative 1. Cosine is 0. We end up with a negative there. Let's plot 11 pi over 6. Sine of 11 pi over 6 is negative because sine is negative in quadrant 4. Cosine of 11 pi over 6 is positive and has the value root 3 divided by 2. Again, negative. So we have negative, negative, that gives us positive. You can see then that we have a local min at pi over 3, a local max at pi, and a local min at 5 pi over 3. Now, the first derivative test doesn't tell you anything about the endpoints. Stating our conclusions, we'll say f has a local min at x equals pi over 3 and x equals 5 pi over 3. F has a local max at x equals pi.